Okay, page 310, PET scanning. Right, there's your syllabus. I take it from this place. You want to be it's like a correspondent course. They are from England and teaching A level. About you have to pay about $400 per year. But you can go for 8 topics without paying. Okay, let's make a start. Medical imaging, positron emission tomography, PET for short, is more expensive and complex than other body scanning technologies. We have studied ultrasound, we have studied X-ray. So this is more expensive, PET scan. That is because like CT scan or magnetic resonance imaging, MRI, which display the anatomy of the body, PET makes metabolic activity visible. That's the difference. Make metabolic activity visible using short-lived radioactive substance called radiotracers introduced into the body. It's taken from here. Since then, PET has become an invaluable tool in oncology, cancer research, cancer treatment, often leading to more accurate cancer diagnosis, the detection of recurrence of diseases, and a better assessment of how patients respond to treatment. Okay, radio tracers, what are they? Radio tracers is defined as substance containing radionuclide that is introduced into the body. Right? Introduce a substance into the body, or substance containing radioactive nuclide that is absorbed. Either introduce it or it's absorbed. No need to write both. If they ask you what is radio tracers, either one. Substance containing radioactive nuclide that is absorbed by the tissue being studied. Radioactive isotopes such as technetium-99m or fluorine-18 are suitable for this purpose because they both bind to organic molecules such as glucose or water, which are readily available in the body. Technetium-99m has a short half-life of 6 hours. It is short-lived form of technetium-99. Fluorine-18 has an even shorter half-life of 110 minutes so that the patient is exposed to radiation for a short time. Right? We don't want to expose the patient to unnecessary radiation. That's why we use short half-life. This one is even better. This one is less than 2 hours. Right? So as little exposure to radioactivity as possible. That's why we shoot short half-life. Using tracers in PET scanning, positron emission tomography, PET for short, is a type of nuclear medical procedure that images tissue in organ by measuring the metabolic activity of cells of the body tissue. A common tracer used in PET scanning is glucose molecule with radioactive fluorine attached called fluorodeoxyglucose. Fluorine nuclide undergoes beta plus decay, emitting positron, beta plus particle. The radioactive tracer is injected or swallowed into the patient and flows around the body. It's either injected into the patient or you swallow it and flows around the body. Once the tissue and organs have absorbed the tracer, right? The tissue or organ that is of interest absorb the tracer, then they appear on the screen as bright area for diagnosis, right? So that they appear on the screen, CRO screen, as bright area for diagnosis. Usually, these days, people don't put full stop, even though it's understood there's a full stop there. This allows doctors to determine the progress of a disease and how effective any treatment has been. Tracers are used not only for diagnosis of cancer, but also for heart and detecting areas of decreased blood flow and brain injuries, including Alzheimer's and dementia. Write down the nuclear decay for beta of fluorine 18 by beta plus emission. You should be able to write the decay, right? If you don't know the product, one is beta plus, the other product is X, call it X. They don't expect you to remember the product, right? So you should be able to write that equation. And then there's a positron. Positron and electron, they will combine and annihilate, produce two gamma rays. Annihilation in PET scanning. Process of annihilation. When a positron is emitted from tracer in the body, it travels less than a millimeter before it collides with the electron. Right? It's unstable, so it looks for electron. Positron and electron will annihilate, and their mass becomes pure energy in the form of two gamma rays, which move apart in opposite direction. Annihilation doesn't just happen when electrons and positrons annihilation. Annihilation is defined as when a particle meets its equivalent antiparticle, they are both destroyed and their mass is converted into energy. Right? Memorize it. When a particle and antiparticle meet, they are destroyed and they produce two gamma rays. As with all collision, mass, energy, and momentum are conserved. Right? There is a electron, there's a positron, they meet, they annihilate, they produce two gamma rays. Right? Annihilation of positron and electron to form two gamma rays, photon. Remember, initial momentum, right? Same mass, same speed. So initial momentum is zero. Final momentum also must be zero. That's why you need two photon. Right? Final total momentum of two gamma ray photon are zero. That's why there are two of them, one in opposite direction. Gamma ray are emitted in opposite direction. Right? We must remember these two formulas that we are going to use. Right? Momentum is energy divided by speed of light, or E equals mc squared. Positron emission tomography scanning, PET scanning. Once a tracer is introduced to the body, it has a short half-life. So it begins emitting positron immediately. This allows for a short exposure time to the radiation. Short half-life, exposure time is also short. So don't expose your patient to unnecessary radiation. A short half-life does mean that the patient needs to be scanned quickly, and not all hospitals have access to expensive PET scanners. PET scanners are expensive, so usually the administrator will have to decide whether they can afford to have one or not. In PET scanning, positrons are emitted by decay of the tracer. They travel a small distance and annihilate when they interact with electrons and the tissue. This annihilation produces a pair of gamma rays photons which travel in opposite direction. Okay. Let's say there's a tumor there. That one emits a tracer, emits a positron, combine. It annihilates with an electron a short distance away, about 1 millimeter, and produce two gamma rays in opposite direction. So there's a detector, gamma ray detector. That's where you introduce by injection or swallow. Annihilation of positron and electron is the basis of PET scanning. Right? That's your PET scan. The patient lays stationary in a tube surrounded by a ring of detectors. That's your ring of detectors. Right? That is your PET machine. There's a rotating scanner. There's a motorized examining table, can slide in, slide out. So you slide the patient to where you want to monitor. Right? This is a brain scan. Images of a slice of the body can be taken to show the position of the radioactive tracer. Right? Like this image, right? This is the image. Detector consists of two parts. Crystal scintillator. When a gamma ray photon is incident on the crystal, an electron in the crystal is excited to higher energy level state. An excited electron travels through crystal and it excites more electron. I think there's something wrong with this statement. It's not an excited electron. Excited is still not liberated. If it's ionized, it's liberated. Then it can cause more ionization. Right? Like this case there, high energy photon collide with the atoms in the crystal, produce your electron and now low energy photon. Right? This is your photocathode. Right? Photocathode, so where an electron hits a cathode, it photo, it produce light, light energy, and light energy, right? You produce a series of electron, multiply. If it's weak, that's why you need a photomultiplier to multiply the number of electrons so that a large current is detected. When the excited electron move back down to the origin state, right? It's higher energy level, we move to a lower energy level, electromagnetic direction is released. The loss of energy is emitted as visible light photon. Right? So that's the choice. The crystal is chosen so that it emit visible light photon. That's the reason for the photocathode. Right? Same like your photocell when we study photoelectricity. Right? That's your CT scan. That's your PET scan. Okay, you are interested to read more. That's your reference. Right? That's your patient. Right? That's your tumor. Patient on the crowd. Activated gamma ray detector. Right? Where the gamma is detected, metered. Right? These are all gamma rays detector. These two are gamma rays. That's a tumor. Photomultiplier, the photons produced by the scintillator are very faint. So they need to be amplified and converted to an electrical signal by a photomultiplier tube. Okay, next part, we detect the gamma rays. So creating an image from PET scanning. Gamma rays travel in straight lines in opposite direction when formed from positron electron annihilation. Okay, gamma ray is not deflected, it's not disturbed by atom or all that, it travels in straight line. This happened in order to conserve momentum, right? We have gone over that, conservation of momentum. That's why we have two gamma photon. They hit the detector in line known as line of response, right? Both in opposite direction. The tracers will emit lots of gamma rays simultaneously, and the computers will use the information to create an image. Two gamma ray photons travel in opposite direction. Gamma ray photon detected outside the body of the detectors. Right? Gamma rays as emitted by the body is detected by detectors. Gamma ray photons arrive at detector at different times, depending on which part of the body the gamma ray are from. Right? Whether deeper or on the surface there, determine the location of the production of X-ray. So the timing will allow us to determine where the gamma ray originated or the location of gamma ray. Image of tracer concentration in the tissue produced. Right? So in this case, the image of the tracer concentration in the tissue is produced. So if there's a lot of activity, then the image will show up there, showing the image there. Calculating energy of gamma ray photons. In the annihilation process, both mass energy and momentum are conserved. They are just repeating the same thing. Gamma ray photon produced have an energy and frequency that is determined solely by the mass energy of the positron electron pair. Energy E of photon is given by, right? Energy of the photon is HF, right? We think of electromagnetic radiation as particle. So photon energy HF, and you convert it to energy is MEC squared. Right? This is where the electron or positron is used, energy of electron or positron. Momentum P is given by P equals to E over C, where ME is mass of electron or positron, H is Planck constant, F is frequency of photon, C is speed of light in vacuum. Okay, you should be able to calculate this one. Give you a time to look through. Fluorine 18 decays by beta plus emission. The positron emitted collides with an electron and annihilates, producing two gamma rays. Calculate the energy released when the positron and electron annihilate. Calculate the frequency of gamma rays emitted. Calculate the momentum of one of the rays. Okay, give you a time to go write the question before I give you the answer. Can you hear me or not?
Yes.
Okay. Because my speaker is a bit problem now. Worried they may not hear me. Right? So the first one is electron and positron collide. So we find the mass of energy of the electron and positron. That's why we have two. Right? There are two of them, electron and positron. Mass of electron or positron, speed of light. Right? For data sheet, there's the mass of electron, the speed of light. Got that. Calculate the frequency. This energy produced two gamma rays. Energy of each gamma rays. Right? There's two gamma rays. So each of them will be divided by 2. Then you should be able to convert to electron volt if you want. Calculate the frequency of gamma rays emitted. Energy appear as gamma rays of energy E equals hf. Right? Frequency is energy divided by Planck's constant. Anything not clear? Anything you need to clarify?
No.
Okay. Calculate the momentum of one of the gamma rays. Right? This is the value we have calculated. Momentum is E over C. Okay. Any comment?
No.
Okay, let's carry on then. What is a tracer? Can you remember
Uh,
or refer to your note? No?
Small amount of radioactive isotope.
Radioactive substance that can be absorbed by a tissue in order to study the structure and function of the organs in the body. Right? Absorbed or introduced in the body. What is annihilation?
Particle meeting antiparticle.
When a particle meets its equivalent antiparticle, they are both destroyed and their mass is converted into energy, to gamma ray photon. Explain the principle behind the use of PET scanning, imaging internal body structure. Right? Patient lays stationary in a tube surrounded by a ring of detectors. The radioactive tracer is injected or swallowed into the patient and flows around the body. Tracer example fluorine nuclide undergoes beta plus decay, emitting positron particle. When a positron emitted from the tracer in the body, it travels less than a millimeter before it collides with the electron. Nothing much, just memory work. The positron and electron will annihilate and their mass becomes pure energy in the form of two gamma rays, which move apart in opposite direction. More photons from a particular point, the more the tracer that is present in the tissue being studied. And this will appear at bright point on the image. An image of tracer concentration in the tissue can be created by processing the arrival time of the gamma ray photon. Okay, let's summarize.
Yeah.
Images of a slice can be taken to show the position of the radioactive tracer. Right? So in a sense, it's like 3D. Okay, this one you can do. Let me see. I think during the break, I will let you try this partial question. We will
Okay.
We will not, I will not solve for you lah. I will solve for you in the next 40 minutes lah. So make sure you try
Exercise 24.3.
We will go to our last topic, astronomy and cosmology. Okay, page 317. What are we going to study under astronomy and cosmology? Standard candle, stellar radii, radius of the star, Hubble's law and the Big Bang theory. Right? Speed of light, you must know where to find. And Stephen Boltzmann's constant. And then that formula you will study. Okay. So don't need to memorize that, know where to find the Stephen Boltzmann's law, Doppler redshift formula. That's the syllabus. Right? We use a different term in physics and in astronomy. Right? The note is taken from here. Right? That one, as I say, is like correspondence course. Okay, what is astronomy? Astronomy is the study of everything in the universe beyond the Earth's atmosphere. That include objects we can see with our naked eye, like the sun, the moon, the stars, the planets, and the stars. It also includes objects we can only see with telescope or other instruments, like far away galaxies and tiny particles, and even include questions about things we can't see at all, like dark matter or dark energy. Don't be troubled by dark matter energy. How about cosmology? Study of nature and the origin of the universe. Right? That's taken from the dictionary. Cosmology, field of study. Where we got 10 more minutes. Field of study that brings together the natural science, particularly astronomy and physics, in a joint effort to understand the physical universe in a unified whole. Right? We use physics and observation from astronomy to try to understand space science or that space. The observable universe is a region of space that humans can actually or theoretically observe with the aid of technology. It can be thought of as a bubble with the Earth at the center. It is differentiated from an entirety of universe, which is a whole cosmic system of matter and energy, including human race. Unlike observable universe, the universe is probably infinite and without spatial edges. Okay, the first term that you need to remember is luminosity, which we study in physics as total power. Luminosity L is the total power of radiation emitted by a star. Right? Another name is power. By astronomy, you call it differently. They call it luminosity. So you need what? An object of known luminosity is a standard candle. In astronomy, a standard candle is a source that has known luminosity. Solar luminosity, LS, there's the sun, the sun's luminosity we can measure from the Earth. Okay, there's the sun there. We can calculate the luminosity. We can calculate the luminosity by measuring the F lah, which we introduce in a while, which we call intensity F for physics. We can measure on Earth. If our Earth is here, we can measure the intensity and then calculate the luminosity of the sun or the star. The best way to picture this is the luminosity is the total radiation that leaves the star. Radiant flux intensity F is the amount of radiation measured on Earth. Which we physics we call it intensity lah. By astronomy we call it radiant flux intensity. By the time the radiation reaches the Earth, it will have spread out in great deal. Therefore, it will only be a fraction of the value of the luminosity. Right? There's the sun or the stars. It emits in all directions. So where it reaches the Earth, we measure just a small bit only of the intensity, and then we calculate the luminosity from the measurement of intensity. Intensity, we know the distance of the sun from the Earth, and we can calculate our luminosity L. Okay, we define our next term, radiant flux intensity F, which physics we call it intensity I lah. Don't ask me why the astronomers and the physicists don't agree with the symbol lah. Radiant flux intensity F is the total amount of energy that crosses normally per unit area per unit time. Right? Remember the beams are parallel. So energy passing the area divided by time, or power divided by area. A is area. Unit of flux is measured in joule per square meter per second, or watt per meter square. Any comment or any question to ask?
No.
Okay, then we carry on. Radiant flux intensity. The flux of an astronomical source depends on the luminosity of the object and the distance from the Earth, according to the inverse square law. This is called, wherever you got R square, it's called inverse square law. F is the flux measured at a distance R. L is the luminosity of the source. R is the distance to the source. Okay. Example, there's a source now. We measure on Earth, so that's the distance of the Earth. Assume no energy is absorbed between the source and the sphere of radius R. Right? In the space between them, where we measure the flux. The flux, there is no absorption there. Right? To understand the inverse square law, when the light is twice as far away, it has spread out 4 times the area. Right? That's the original area. Distance R is twice the radius, twice the distance, sorry, not the radius, twice the distance. It has spread out to 4 times the area. Right? So the intensity has become I over 4. So you have reached 3R, then it has spread out to 3 square. 3 square is 3 area. right? 9 area, 9A, but intensity is reduced by I over 9. Light sources which are further away appear fainter because the light it emits is spread out all over the greater area. Right? Remember, it's not parallel light, it's spread out all over the area, right? All over in different direction. We only measure a small area. That's all. So it's not parallel, it's parallel, then we don't have to worry about all this calculation. But because it's spread out in all direction, we have to use a inverse square law. Right? The further it is, same area, intensity has reduced to 1/9. It is 3 times the distance. The moment the light leaves the surface of the star, it begins to spread out uniformly through a spherical shell. Right? There's a spherical area of spherical shell. So all this energy is spread out over this area. Surface area of sphere is 4 pi r square. Standard candle. Standard candle is defined as memory work, an astronomical object which has a known luminosity due to a particular characteristic quality possessed by that class of object. Example of standard candle are surface variable stars, a type of pulsating star which increases and decreases in brightness over a set time period. Right? When we call it brightness, we mean intensity. Radiation has a well-defined relationship to luminosity. And then type 1A supernova. Supernova explosion, including a white dwarf. The luminosity at the time of explosion is always the same. Okay, that's the standard candle approach. If you know you have the same source strength of light, then counting the number of photons through a standard area detector tells you the distance from the source. Right? That example there, there's the area there at a distance r away, 16 photons coming out. Right?